Good morning. Today would be a very productive day for all of us because we get to start learning about electrical machines. And we will explore DC machines or direct current machines in our first lesson under electrical machines, your subject, or ELC 203. All right, and I hope I can give justice to the topic. I will be presenting to you, and at the end of this presentation, I hope that everybody will be able to, to do the activities uh, which I have prepared for you to comply. All right. Let me start my conversation or my presentation about electromagnetic conversion. When I talk about conversion, meaning imo i-convert, all right? Imo i-convert. You have to convert from electrical to mechanical or vice versa, from mechanical energy to electrical energy. Because, in as far as electrical is concerned or energy is concerned, energy is very much needed in different forms, okay? Everything needs energy. Just like us, we do need energy. Otherwise, we cannot move or we cannot act or we cannot do what we are expected to do because we lack of energy, right? But going back with the lesson proper, energy is needed in different forms. It could be light or bulbs or light bulbs or heater, which needs electrical energy. Fans, the rolling mills, the like, also needs mechanical energy. And so that is why I said earlier that energy is different or is needed in different forms. It could be light, it could be bulbs, heater, etc., fans and rollings. Now, uh, in every purpose, okay, whatever purpose of that certain things or, like bulb, etc., it also needs a different forms of energy. All right. Now, when we talk about conversion from mechanical to electrical, uh, we will use generator, right? And then comes out of it is electrical energy now. All right. The and continuous energy converter are called electrical machines. And EC or alternating currents or what we known as electric supply. This is an electric supply that is just like what we are using right now in every household. We are using the electric supply coming from the alternating current, all right, from the alternating current. And AC machines, it could be synchronous or asynchronous, right? When we say synchronous machines, it constitutes both synchronous motors as well as synchronous generators. In other words, it could be asynchronous motors or as synchronous generators. An AC generator or an AC system has some advantage over DC system. We know what is DC, right? DC or stands for direct current, right? Direct current. Again, an AC system has some advantages over the DC system. Therefore, the AC system is exclusively used for the generation, transmission, and distribution of electrical power. The machines which converts mechanical power into AC electrical power is called a synchronous generator or alternator. Again, the machines which convert mechanical power to AC electrical power is called synchronous. That is why we enter the AC electrical supply, AC machines, enclosed of that is synchronous or asynchronous motor or generator. Again, so AC, the machines that converts mechanical power into AC electrical power is called synchronous generator or alternator. However, if the same machine can be operated as a motor. It is known now as synchronous motor. All right. Now, electromechanical energy conversion use a magnetic field as the medium of energy conversion. And electromechanical energy conversion device converts electrical energy into mechanical energy, or converts mechanical energy into electrical energy. And there are different, what is the difference between synchronous and asynchronous? Okay, let's look at in total, or one by one. Okay, and these are the differences. Now, if we say synchronous, synchronous means motor. A synchronous motor is a machine whose rotor speed and the speed of the stator magnetic field is equal. Okay, the speed of rotor and the speed of stator is equal. If it is asynchronous, the rotor rotates at a speed less than the synchronous speed. Again, see the difference? If it is a synchronous motor, rotor speed and the speed of the stator magnetic field is equal. When it is a synchronous motor, the rotor rotates at the speed less than the synchronous speed. Now, then if it is a synchronous motor, it does not have slip, right? The value of slip is 0. But if it is a synchronous motor, it has slip. Therefore, the value of slip is not equal to 0. Okay. Then, slip ring and brushes. If it is a synchronous motor, the slip ring and brushes are required, while in asynchronous, it is not required. Okay. Then, when we talk about cost, ang presyo, no? Synchronous motor is costly, right, as compared to a synchronous motor, because asynchronous is lesser. The value or the cost of a synchronous motor is less than the value of asynchronous. So it's more cheaper. If we are going to say it using our own parlance, mas barato ang asynchronous. And when it comes to efficiency, the synchronous motor efficiency is greater than asynchronous. All right? This is meaning to say that synchronous motor is more efficient than if we are going to compare it to the asynchronous motor. Right? And when it comes to power factor, a synchronous motor, by changing excitation, the power factor can be adjusted according as lagging, leading, or unity, while in a synchronous motor runs only at the lagging power factor. Okay, these are some explanation or some description of each motor. Each motor, either synchronous or asynchronous. When we talk about its differences, what is the difference between synchronous motor and asynchronous motor? In terms of cost, synchronous is more, costly than compared to asynchronous. But when we talk about efficiency, synchronous motor are more efficient than the asynchronous motor. All right, then. Okay, so synchronous motor is a machine whose rotor speed and the speed of the stator magnetic field is equal. I am just repeating what I have said earlier. Okay, the stator and the rotor of the synchronous is equal, but if it is a synchronous motor, the rotor rotates at a speed less than the synchronous speed. All right. So, moving on. Now, these are the structural, or we see the flow, for giving you some of the difference between DC and AC machine, okay? When in terms of electrical machines, okay? When we talk about DC machines, it is field winding and permanent magnet. What do you mean by field winding? It is the insulated current carrying coils of the field magnet that produce magnetic field needed to excite a generator or motor. In its coil, it is energized in turn. The rotor aligns itself with magnetic field produced by energized field winding. And we know what is a permanent magnet. Now, AC machine, however, again, this is about synchronous machine, right? And induction machine. If you can remember, as what I've said earlier, synchronous machines, the stator and the rotor, you know, has an equal speed, all right? Again, electrical machine, the synchronous machine whose rotating speed is proportional. It is proportional. It is proportional to the frequency of alternating current, right? An induction machine, an induction motor, or asynchronous, okay? It's one, a synonym of asynchronous is induction motor, okay? It is an easy electric motor in which the electric current in the rotor needed to produce torque is obtained by electromagnetic induction from the magnetic field of the stator. Now, all right. I will just run through this. Anyway, you can just review some of the presentation after the lesson. Two electromagnetic phenomena in the electric machines. One, conductor moving magnetic field, or a motional voltage. To find it, the formula is E is equal to BLV, where B stands for magnetic flux density, and I stands for length of the conductor cutting the field, and V is the speed at which the conductor cuts the field. Okay, both phenomena occur simultaneously in energy conversion process. All right, then to find the current carrying conductor in magnetic field, or the electromagnetic force, the unit is Lorentz force. The formula is F is equal to BLI, where F is the force of the conductor, or the force on the conductor, and L is the length of the conductor, and I is the current flowing through the conductor. Electric machines construction. This is how the machines or the parts of the electric machines. One, we have the stator and rotor. It's with ferromagnetic materials. This is composed of ferromagnetic materials. Then slots, of course, with conductors. Cylindrical machines, which has a uniform air gap. Then salient pull machines, or the letter B, is non-uniform air gap. Iron core, maximum flux density. Laminations, which reduce the eddy current, and conductors interconnected to form windings, and of course the armature winding, in which voltage is reduced. Field winding, the one that produces the primary flux. These are the constructions of electric machines. Now, and some basic about DC machines, the recurrent general action, an EMF, or electromagnetic force voltage, is induced in a conductor if it moves through a magnetic field. Then motor action, there is this motor action, which is a force is induced in a conductor that has a current going through it and placed in the magnetic field. Any DC machines can act either as a generator or as a motor. All right. Next, some again fundamentals about direct current machines. It is most often used as for a motor. Okay, direct current is often used for a motor, and the advantage of DC machines are it is easily speed and torque regulation. And however, their application is limited to mills. Okay? Limitado ra ang ilang application. Magamit ra sila sa mills, mines, and trains. As examples, trolleys on underground subways, cars may use DC motors. In the past, automobiles were equipped with DC dynamos to charge their batteries. But even still today, the starter is a series DC motor. However, the recent development of power electronics has reduced the use of DC motors and generators. And electronically controlled AC drives are gradually replacing the DC motor drives in factories. Nevertheless, a large number of DC motors are still used by industry and several thousands are sold annually. And the variable speed, large and small power range. Field winding carrying DC current is a stator produced flux symmetrically distributed, but pole axis equals direct D axis. Armature winding in rotor, alternating voltage is induced, and mechanical commutator brush assembly rectify the value to become DC. Okay. The stator, one of the structure or construction or parts of DC machines, is a stationary part of the machines. It carries a field winding that is used to produce the required magnetic field by DC excitation, often known as field. And the rotor or the rotor is the rotating part, okay, found in the center part of the machines. The rotor carries the distributed winding. There's a winding in it, right? And is the winding where the electromagnetic force is induced, also known as armature. And this is how DC motor stator with poles look like, right? And the other one is the rotor of the DC motor. Okay? This is the DC rotor motor of armature, or the rotor of DC motor, and this one is the DC stator with poles. Okay, muna niya siya sa gawas na kanimo dire sa sulod. Alright. Then these are the details. We have the mica insulations, insulated, this one, and the copper inductors. Mica insulations between segments, copper segments. Then, when the torque passes the interpolar region, okay, the in-touch brush B1 current flows from B2 as shown in the figure below. All right. The torque in short circuit, figure B, voltage 12. The current in torque. Then again, we continue. These are the armature windings. Larger machines have more than 2 poles. Most of the conductors are in region of high flux density. Now, kung ingutang full pitch, this is the distance between the center to the 2 adjacent poles. 108 is equal to 180 degrees. Coil pitch, distance between 2 sides of a coil. Full pitch, coil pitch is equal to full pitch. Short pitch, coil pitch, less than pole pitch, mainly in AC machines. All right. Then this is the lap winding, armature lap winding. One coil between 2 adjacent commuters bars. Okay. Then I will just run through with this. These are the wave winding. We will discuss this more on this as we come along, as we continue to discuss our subject, the lesson that we will be having along the way. Then Armature winding voltage. These are the formula for finding the armature voltage. The voltage induced in turn is equal to the total voltage is equal to BLB, etc., etc. All right. Anyway, you can have this formula as we go along with the subjects. If there are problems or problem solvings that needs to be solved, these are the formula that we are going to use. All right. Some activity will be given, as we go along. Armature torque. Then these are example. All right. Example 1, I'll give you an example. A 4-pole DC machine has an armature of radius 15 centimeter and an effective length of 30 centimeter. The poles covered 75% of the armature periphery. Right? The armature winding consists of 35 coils. Each coil having 7 turns. The coils are accommodated in 35 slots. The average flux density under each coil is 0.85 T or turn. All right. Then the problem is if the armature is not wound, determine the armature constant, or the symbol is key with small letter A. Determine the induced armature voltage when the armature rotates at 1000 RPM. Then determine the current in the coil and electromagnetic torque developed when the armature current is 400 amperes. Determine the power developed by the armature. All right. So these are the given one. Okay. Atong pag-solve. Okay. All right. These are the computation below. And the second example, if DC machine example is wave 1, we put parts A minus D, and these are the result, the formula. Okay, you can review this afterwards. All right, and more of these problems will be given for you to solve. Okay, now let's talk about magnetization. It's a field MMF on D axis. It is a magnetic core with infinite permeability at low values of flux. Okay, and it is assumed material UR infinite permeability, reluctance in the air gap only. Again, ako na po na continue because you will have more of this as we go along. Magnetization curve. It is more convenient if the magnetization curve is expressed in terms of armature induced voltage. Just run through this, and this is the curve, magnetization curve. If it is a residual, it is shown at figure at the upper portion, the right upper portion, the right corner. Then induced voltage, this field current here, and these are the graph that shows us the curve of magnetization. Now, there are classification of DC machines. One is the field circuit and armature circuit can be interconnected in various ways to provide a wide variety of performance. Okay, and the field poles can be excited by 2 fields winding. Then the shunt winding has a large number of turns and takes only a small current, or less than 5% rated armature current. The series winding has fewer turns but carries a large current. If both windings are used, the series winding is wound on top of the shunt winding. And of course, these are the classification of DC machines: separately excited machines, series machines, shunt machines, compound machines, which are all self-excited generator, which is needed in residual flux machines. Permanent magnet can be considered as separately excited but constant excitation. Right? Moving on. Again, Sultin na nato ni earlier. Generators characteristic, BI characteristic of DC generators. Okay. Example number 3, and these are the formula. A lap-wound armature is used in a 6-pole DC machine. There are 72 coils in the armature, each containing 12 turns. The flux per pole in the machine is 0.039, and the machine spins at 400 RPM. Determine the induced voltage. How to find that? These are the formula. Z is equal to 2N equals, okay, 2 times 20, 2 times 20, 12, 168, and so on and so forth, right? Then, example 4, you will be the one who will compute this example 4, okay? Just follow the formula that is given a while back, the previous slides, study it carefully, and you can come up with the answer of example number 4. Okay? That's all for now. God bless.